So we talked a bit about the requirements for homework 5, and actually we should have covered most of what you need to know in order to complete homework 5. That means that the next thing that we need to talk about is how to deal with the challenge assignment. And one of the main things that you'll have to deal with the challenge assignment is actually implementing these shell operators that we talked about in the previous video. So the first shell operator that I want to talk about is the redirect operators. We have redirect input and redirect output, and they both work kind of the same way. So what I'm going to do is I'm going to write a program that does a redirect, although it doesn't do it, it's not a shell, but it's going to execute a program with one of its standard streams redirected to instead operate on a file. So to do that, open up a file called redir.c, and we're going to go ahead and include some headers here. You should recognize these headers because they're a pretty close set of headers to the fork example that we did earlier. And the reason for that is that in order for this plan of doing a redirect to make sense, we want to have two processes, and in the parent process we're going to fork, same pattern as before. We're going to have an if statement with if cpid equals fork is the condition, and then we're going to have an if and else branch, and as before, this is the parent and this is the child. And I normally get a question around this point asking, why do I put double parens here around the cpid equals fork statement? And the reason for that is because compilers like to be helpful. And if we have an if statement, and in the condition of the if statement we have a single equals in C, that is almost always an error. We usually meant to type double equals. But in this case, I definitely didn't mean to type double equals. The thing that I want to do is I want to call the fork function. Fork is going to return a value. I want to assign that value that it's returning to the cpid variable, and then I want to take the result of that assignment operation as the value that we're considering in the if statement. Because if that value assignment in C returns the value that was assigned, and if that value is 0, we're in the child, so I want to go down here. So I really mean if, and then an assignment in the condition, but to get the compiler to be sure not to complain about it, I'm marking this as being special by just putting another layer of parens. And that will also cause a human looking at this to say, wait, this looks funny. I mean, this looks funny because it's single equals in an if, but it also looks funny here. Maybe that means that the person who wrote this meant what they wrote and this isn't actually a mistake. So in any case, we have a parent and a child, and in the parent what I'm going to do is I'm going to say waitPid on the child PID. I don't care about the status, I don't care about options. And when we're done, we're just going to print our process ID and that the child is done. In the child process, I'm going to go ahead and say int fd is open. And I'm going to create a new file called standardout.txt, create or append or, and then 0644, same reason as before. Oh, so another question that I potentially get is, why are we using bitwise OR here to specify flags? Let me actually do a little bit of a digression on that. So the open function here takes flags as an integer. And what we'd like to be able to do is pass a bunch of Boolean values into this system call. We'd like to be able to pass this bunch of Boolean values in a single register. Now, an int in C is a 32-bit integer, at least on AMD 64 Linux. And so by specifying that we have an int called flags, that actually gives us 32 bits. And so if we use individual bits to specify these flags, it might be that the flags are write only is 1, append is 2, creat is 4. So these are each powers of 2, which means they're represented by an integer where only one single bit in the value is set. And so if we OR them together, that's going to give us a value with multiple bits set. And if I OR those two together, 1 OR 2 is the same as 1 plus 2, because in both cases only one bit is set. And so we get the sort of union of the bits set. So this is the integer 3, thus representing that these two flags are set and no other flag is set. And then it's actually really easy to test whether this is set. So if I say int x is those two things, then I can ask if x and we can immediately test to see whether that flag was set. So this gives us a really simple way to specify this like set of Boolean flags as a single integer. This is a common pattern that we'll see in all kinds of low-level programming, but this is a good example of a place where it's happening. So that's what's going on with this this bitwise OR to specify flags. All right, so that's a distraction from what we were trying to talk about. So we're going to open this thing, and so now we have this file descriptor open to this newly created file, temp_standardout.txt. Now the next thing that we're going to do is we're going to close file descriptor 1. Now you'll remember file descriptor 1 is standard out. By default, we expect standard out to be hooked up so that if we print things to standard out, they'll show up on the screen. They'll print out in the terminal window. And if we close that, then that file stream that prints out to the terminal window, or wherever standard out went before, is now gone. So if right now we print to standard out, we're going to get error file is closed. But there's a neat system call called dupe. And what dupe does is it duplicates a file descriptor. And so we can say dupe fd, we pass it a file descriptor, and it's going to create a copy of the file descriptor using the lowest numbered unused file descriptor for the new descriptor. Now we just closed 1. We know it's in 0. 0 is standard in, so 0 is used. But we just closed 1, so 1 is available. 1 is therefore the lowest number that's available. And so this is going to copy the standardout.txt file descriptor into slot 1, making it standard out for this process. Once we've done that, we can actually close fd because we have a copy of the open stream to standardout.txt. So we can close file descriptor, the file descriptor that was in fd. This is the integer 4. We know that 0, 1, sorry, it's the integer 3. 0, 1, and 2 are taken by default file descriptors. So if we open another file, it's going to be 3. We duplicate it, it becomes 1, we close 3, and now this process has 3 open file descriptors. Standard out is the default probably from the keyboard. Sorry, standard in is the default probably from the keyboard. Standard out is this standardout.txt that we just inserted into the file descriptor table, and file descriptor 2 is still standard error. So at this point, we've done the operation of replacing the standard out for this process. And at this point, if we do exec lp echo executed echo null, then the echo command is going to run in this process, the same process where we just did this file descriptor or file descriptor table manipulation. And it turns out that file descriptor tables are one of the things that is process state that's preserved across exec. The only place we get these default file descriptors is from inheriting them from our parent. So whatever our parent gives us is what we get. So then we can go ahead and say return 0. And now, if we run this redirect, it's going to say child done. But if we say cat temp standard out.text, it is failing to work for some reason. So let me go ahead and remove standard out.text. And then make sure that if we run redirect, my example is not working. This should work. So we close one. We're opening the file, create append read only. Sorry, write only. Read only would not work. Let's go ahead and just start debugging, because that's what we do. So assert is a thing that lets us check that conditions are true and otherwise crash. So I'm going to say assert cpid does not equal -1. And then we're going to say assert fd equals 3, just to make sure that I understand what's going on. I'll say make and run redir. And that still works. So standard out.text is getting created. But our echo command is not actually doing the right thing. And the reason for that is because I left out a comma, which apparently isn't a syntax error. I think the mechanic in C is that if you have two strings that are just sort of next to each other with nothing between them, they get sort of magically concatenated into one string, which is a useful trick for the preprocessor, but means that in this particular case I didn't get a coherent error message. But in any case, now that we fixed that comma issue, we get the correct behavior, which is that we've successfully redirected our standard out to a file, and that state is preserved through exec. So when we run this echo command, it is then going to print to that file, even though we don't even control the source code for echo. That's just a system command. Now, following the same sort of pattern, we could do a redirect input. So instead, for a redirect input, we close 0, and then we open something for reading, and then we dupe the thing, and then after that we redirected the input. So that is how redirecting input would work. The next example that's kind of similar that I want to show is how we can do a pipe, or what is a pipe? So for that, I'm going to have to write a slightly more complicated program, but we're just going to go ahead and do that. Now, when we're dealing with system calls, it's good to check the return values. Most system calls return -1 on failure, and if they fail, they actually are going to give us an error code which indicates what the failure was. So this check_rv is a utility function that's going to take an integer that we got back from a system call. Most system calls return an integer. We're going to say if the return value is -1, we're going to exit 1, because we don't want any of our system calls to fail, but we're also going to use this p_error function. And p_error is kind of neat. It's part of the sort of Linux standard library. And what it's going to do is it's going to produce a message on the standard error stream describing the last error encountered during a call to a system or library function. So a system call just failed, we know because we got -1 back from it. And p_error is going to print out the text fail, followed by an error message from the system call that just failed. And that could be helpful for debugging. All right, now our main function, int main, int argc, char pointer argv is an array and returns 0. Now, a pipe is a thing that we can create with the pipe system call. And the pipe system call has this sort of funny signature where it takes an array of 2 elements as its input. And for our purposes, that means it's going to take the pointer to the beginning of an array, but the syntax ends up just being that we can go ahead and declare an array of 2 items on the stack and then pass that variable in as the first argument to pipe. And what pipe is going to do is it's going to fill in that array with 2 file descriptors. The rule is anything that gets written to the right end of the pipe, which is index 1, will then be readable from the read end of the pipe, which is index 0. And it is sort of, one way to remember this is that the pipe index that you read from is 0, the standard file descriptor you read from is standard in 0, the end of the pipe that you write to is 1, the standard file descriptor that you write to is standard out, which is 1. So it's the same as standard out. What you do with it is the same as standard out and standard in. But in this particular example, I'm going to go ahead and make it real clear that the read end of the pipe is pipe fds 0, and the write end of the pipe is pipe fds 1. That way we can't get too confused. Then we're going to write, we did a system call, so we want to do check_rv just to make sure that our system call succeeded. So we're going to write to the right end of the pipe our message. All right, so we've written that message to the pipe. Then we're going to create a buffer. And then we're going to read from the read end of the pipe into our buffer. we'll go ahead and null terminate that buffer, and then we're going to write to standard out the message that we just sent through the pipe. And the result is that we have a relatively complicated program that's going to print hello. But it does in fact print out the message hello pipe. Now, in this particular example, this is pretty useless. We went ahead and created these two file descriptors and wrote to one, read from the other, and in all that time we could have just printed out the message and the string constant that we assigned right here. But the trick with pipes is that the pipe system call is going to fill in 2 slots in the file descriptor table. The file descriptor table is inherited by child processes, and that means that if we have the write end of a pipe in one process and the read end of a pipe in another process, we can write to the pipe in one process, read from the same pipe in another process. That allows us to do inter-process communication using file descriptors, which could conceptually be pretty powerful. So to see that, we're going to have to do another example. So I'm going to copy pipe 0.c over to pipe 1.c, and we're going to go ahead and write the fancier version of this in a new file. So once we have our 2 pipes, the 2 ends of the pipe, we can go ahead and say int cpid. Then we're going to do if cpid is fork, check rv cpid, and then we want to let's go ahead and put our message only in the parent, so it's like clear that we don't have access to it in the child. And then in the child, we're going to do this child stuff. And there's our whole program. So now we have a message that is on the stack only in the parent process. We're going to write it to the pipe. We're going to check the return value, and we are going to then in the child, we're going to read from the same pipe and print it out. There's one important thing that I want to put in this example, because it's something that we always want to do with pipes. Once we've forked after creating a pipe, we want to close the end of the pipe that we're not going to use in both of the sort of post-fork processes. So this parent process never uses the p-read end of the pipe. This child process never uses the p-write end of the pipe. If we don't do that, we can end up with sort of awkward situations where our programs sort of freeze or get stuck. And we don't want that, so close the ends of the pipe you're not using. Again, even with 2 processes, we are able to print the same thing. So that is the simple example of those 3 operators, redirect and pipe, at least the tools that we need for it. Of course, in order to make pipe work with the shell, the next step is you have to do the same operation as redirect and trade in these file descriptors that you put in the pipe array into the standard file descriptors for the child process.